Okay, it says which bonds are arranged in order of increasing polarity.
C.
Yeah, so
A.
all of these bonds are between the hydrogen and halogens. Okay, so you have the bond between hydrogen and fluorine, chlorine, bromine, and iodine. And you know that all of these hydrogens, their electronegativity is more than hydrogen. And for the hydrogen, when you are going down the group, the electronegativity decreases. So the most electronegative bond is between HF, then HCl, then HBr, then HI. It says in order of increasing, it means first you have to mention the one which has least polarity, then HBr, then HCl, then HF. So the answer is C. So your answer is correct. Okay. So let's go to question number 2. It says which row correctly describes the bonding type and melting point of the carbon and carbon dioxide. Okay, so we are talking about two types of the material. The first one is carbon, the next one is carbon dioxide. Okay, and it asks about the bonding type and the melting point. So what type of the bonds are available between the carbon molecules and for the carbon dioxide? Two type of the bonds are mentioned here, covalent or ionic. Okay, what about the bonds between the carbon atom? Is it covalent
Covalent.
or ionic? So the bond
Covalent.
between the carbon is covalent, exactly. And for the carbon dioxide, again is covalent. Carbon is connected to the oxygens by a covalent bond. So both of them, the bond type is covalent. But what about the melting point? The melting point not only depends on the type of the bond that you have, but also it depends on the structure. We have two type of the structure here. The carbon dioxide is a molecule, so it's molecular structure. What about the carbon? It has giant covalent structure. Okay, so this is the giant molecule. And you know the attraction between the molecules are weak. So the carbon dioxide has low melting point. Okay, but the attraction between the carbons in the giant covalent structure is a strong covalent bond. So they will have high melting point. So the answer would be A. So here it's comparing two type of the material, giant covalent structure with the molecular material. You know the giant covalent structure has much more melting point than the molecular material because between their base unit, which is atom, you have strong covalent bond. But for the molecular compounds like the carbon dioxide, between the base unit, which is molecule, you have weak intermolecular attraction. So the answer would be A. Okay, so let's move on to question number 3. Again, it's talking about the boiling point. So you can see a lot of question in this section in the IB comes about the boiling point and the attraction between the base unit. Okay, when you want to compare the boiling point, the first thing that you have to check is what type of material do you have? Do you have ionic? Are you comparing the ionic with each other? Are you comparing the metallic compound with each other? Are you comparing the molecular compound with each other? Or you have the giant covalent structure? What do what are you talking about? Uh, what type of the structure do they have? Sometimes some of the questions, they have one ionic and for example, one metallic and one molecular. And they are comparing the boiling point of them, exactly like the question number 2. In question number 2, the question comparing the melting point of the carbon and carbon dioxide. So it's comparing the melting point of the molecular compound and giant molecular compound. So obviously the giant molecular compound has the most melting point among them. But some of the questions, all of the substances which are given from one of them, like this one. So all of these substances that you have here is molecular compound. Okay, so you are not comparing between different type of the material. You have molecular compound and you want to compare their melting point and boiling point. In this case, you must look at the attractions which are available between the base unit of that type of the compound. So in the molecular compound, for example, you have hydrogen bonding, you have dipole-dipole attraction, and you have London dispersion forces, and so on. So these are the main type of the attractions which you have here. Okay, let's come back to this question. Okay, so four type of the molecular compound is mentioned here. One is CH3CH3, CH3CH2Cl, CH3CH2Br, CH3CH2I. So three of them are polar molecule, one of them are non-polar. So which one is non-polar?
CH3, CH3.
CH3CH3, exactly. This is the hydrocarbon. It's non-polar, and the only force of the attraction between its molecule is London dispersion force. But the other type of the molecule, it has the London dispersion force. And also their London dispersion force is more than CH3CH3 because the halogen is more massive than the hydrogen. So they are not only have London dispersion force, which is stronger, but they also, because they are polar, they have dipole-dipole attraction between them. Okay, so these compounds has more melting point than CH3CH3. But if we want to compare this one, both of them, all of them are polar, so they have dipole-dipole attraction. None of them has hydrogen bond, but the halogen molecule is different. Here you have chlorine, here you have the bromine, here you have the iodine. And you know the iodine is more massive among them. So when your molecule has higher molecular weight, it means the London dispersion force for that one is stronger. So here, the CH3, CH2I, it has highest London dispersion force between its molecule, then CH3, CH2Br, then CH3, CH2Cl. And CH3, CH3, it has only London dispersion force, which is big. So if we want to order them in order of increasing the boiling point, the answer would be the A. Okay? So CH3, CH3 is the smallest molecule, and it has only London dispersion force. The rest of the molecule, they have dipole-dipole attraction, but they also have London dispersion force. But this one, because the weight is small, it has least London dispersion force among them, then this one, then this one. Okay, any question here?
Teacher, but isn't chlorine more electronegative than the Br and
Yeah, it's
iodine?
more electronegative than Br. So this molecule becomes more polar than this one. Okay, but they doesn't have great effect. Both of them have dipole-dipole attraction. But because the chlorine is small, bromine is big, it has great effect in the London dispersion force. So London dispersion force is very sensitive to the size or to the mass of the substance that you have.
Okay, thank
Okay,
you.
so that's why when we are looking at group 17 halogen, fluorine, chlorine, bromine, and iodine, so all of them, the only force of attraction between their molecules is London dispersion force. And when you are going down the group, the size of the molecule becomes bigger, the molecule becomes more massive, so the London dispersion force increases. So it increases in a way that the first two is gas, the next one is liquid, and the last one becomes solid. So this shows that the size has great effect on the London dispersion force between the molecules. Okay, so let's move on to question number 4. It says which compound forms hydrogen bonds in the liquid state? So you know that for having hydrogen bond in the molecule, hydrogen must be connected to at least one of the phone elements. And you can see in this molecule, in the B, you don't have the phone elements. You don't have fluorine, oxygen, and nitrogen. So obviously this one doesn't have the hydrogen bond. But for the rest of them, you have oxygen and you have nitrogen. So there is possibility that they form the hydrogen bond. Okay, for this type of the question, you must know the functional groups. As I said several times, OH represents alcohol functional group. So C2H5 is like this. You have CH3, CH2, OH. Okay, so this OH is alcoholic functional group, as you can see here. Okay, so you can see in this molecule, hydrogen is bonded to the oxygen. So this one has hydrogen bond. So the alcohols, they have hydrogen bonding. But what about molecule in C? What is CHO? Again, as I said several times, CHO represents aldehyde. It means C double bond OH. Okay, so this is the CHO. And what is the rest of the molecule? Is CH3. So a CH3 is connected here. So you can see you have hydrogen, but hydrogen is not bonded to the oxygen. So this one doesn't have the hydrogen bond. And part D. In part D, so you have three CH3, CH2 bonded to the nitrogen. So none of these hydrogens are bonded to the nitrogen. So this one also doesn't have the hydrogen bond. If I want to draw this one is derivative of the ammonia. In the ammonia, three hydrogens are connected to the nitrogen. So we have NH3. But here, these hydrogens are replaced by C2CH3. We call it ethyl. So we have CH2CH3 here. And in all of these positions, you have CH2, CH3, CH2, CH3. So you can see in this molecule also hydrogen is not connected to the nitrogen. So this compound also doesn't have hydrogen bond. So the answer is A, alcohols. And for the organic molecules, when you see the alcohols, you must know that there is hydrogen bond there. Any question?
No.
Okay, so if you don't have question, let's move on to question number 5. It says, which species contain a coordinate covalent bond?
A.
Okay, so this one and this one, they are very famous examples. We have talked about them. They have coordinate bond. But let's look at this one. Again, CHO means C double bond OH. And it's connected to one hydrogen. So you have one hydrogen here. Okay, so let's look at each one of the atoms. Okay, hydrogens, they have one bond. Hydrogen never can have coordinate. The hydrogen needs to share one electron to become like the helium, and each hydrogen shared one electron. Carbon has 4 valence electron. It needs to share 4 electrons to become octet, and it shares 4 electron. Oxygen also has 6 valence electron, and it needs to share 2 electron to become octet, and it shared 2 electron. So you can see none of them has extra bond. So this emphasizes that you don't have any coordinate bond here. So the answer is 2 and 3. So the answer is question number C. Okay, so if you draw the Lewis structure, if you remember, for CO it was like this, and for OH3 it was like this. Again, look at this one. Oxygen only needs to share 2 to become octet. But here, the oxygen, this is 2 bonds. It also forms 1 bond. So, and if oxygen, which has 6 valence electrons, shares 2 of them for the bonding to become octet, 2 lone pair must remain for itself. But you can see in the CO, only it has 1 lone pair and 1 extra bond. So this emphasizes that this is the coordinate bond. Same thing here. Oxygen has only 1 lone pair, and it not only have 2 shared electrons, but it has 1 extra bond. So this shows that the next lone pair is shared with hydrogen. So this is the covalent. This is the coordinate bond or dative bond. So the answer becomes C. Yes.
Could you explain HCHO again? I did not understand.
Okay. So CHO means C double bond OH. And hydrogen, one hydrogen is connected to here. So this is the structure of CHO. Okay. So look at the carbon. How many lone pair do the carbon have? 4 lone pairs. Sorry, how many valence electron do the carbon have? It has 4 valence electron. It needs to share 4 electron to become octet. And if you see, it has shared all of those 4 electrons here. So it means it doesn't share a lone pair from one side. All of its electrons are participating in the sharing. And for the oxygen has 6 valence electrons. Okay, so it shared 2 of its electrons here. You can see 1, 2. So how many lone pair remains for itself? 2 lone pair remains for itself. It means none of its lone pair is given to any atom by one side, from one side of that. Okay, so it means it doesn't have the coordinate bond.
Thank you.
Welcome. Okay, question number 6. So a group 2 element A forms a compound with group 17 element B. Which is the most likely formula and type of the bonding in this compound? So because group 2 is metal and group 17 is non-metal, the bond between them must be
Ion.
ionic. Okay, so in the ionic bond, the group 2, they become cation, and the charge of the cation would be A2 plus. And group 17, they have 7 valence electron. They need only 1 electron to become octet, so their anion charge would be B minus. And the ionic bond which forms, this 1 comes here, 2 goes here, so the compound would be A, B, 2. So the answer is B. Okay. Question number 7 says which structure below contain at least 1 double bond? Okay, so you have to draw the Lewis structure to know that. N2, it has 1 triple bond. O2, it has 1 double bond between the oxygen and carbon dioxide. It has 2 double bond inside the molecule. So this is which one has at least 1 double bond? The answer is 2 and 3. So the answer is C. Okay, so this was easy question. Let's move on to the next question. Question number 8 says which molecule according to the VSEPR per theory would be expected to have the smallest bond angle? So which one do you think has the smallest bond angle?
C.
A, H2O.
The A, H2O. Okay, so you have to draw the Lewis structure to predict what would be their angle. So you know that for the water, the Lewis structure is like this. The molecule is bent, and electronic geometry is tetrahedral, but it has 2 lone pairs, so the molecule becomes bent and the angle decreases to 105. In pH3, again, the electronic geometry is tetrahedral. Okay, and you have 1 lone pair, so the molecular geometry becomes pyramidal, and the bond angle decreases to 107. For CCl4, it has 4 domain, so both its electronic geometry and molecular geometry is tetrahedral, and in the tetrahedral, the bond angle is 109.5 degrees. So you can see all of them, their electronic geometry is tetrahedral, but by increasing the number of the lone pair, the bond angle decreases. And for the last one, H2CO, if we draw the Lewis structure for that, it has planar structure. It has 3 domains. And you know, in the trigonal planar structure, the bond angle is 120. So the answer is A.
Question number 9. Which compound is most ionic? HF, KF, CF4 and LIF. So you can see the more electronegative atom in all of these 4 compounds is fluorine, and the fluorine is the most electronegative atom at the top of group 17. So it combines with hydrogen, carbon and sodium, lithium and potassium. So when the difference in electronegativity between two bonded atoms increases, it will have most ionic characteristic. So you know that the ionic trend from the left to the right, the electronegativity increases. So this means the difference in electronegativity between the carbon and fluorine is much less than difference in electronegativity of these elements in group 1 with the fluorine. And when you are going down the group, the electronegativity decreases. It means when you are going down the group, the difference in electronegativity between the element and fluorine increases for group 1. So that's why Kf between these four atoms has the most electronegativity differences with the fluorine, and the bond between them would be the most ionic. So the most ionic compound here is potassium fluoride.
Question number 10 says, which of the following molecule is polar? Cl2. So obviously this one is non-polar. You have two atoms, identical atom, it is non-polar. BCl3 and NCl3 and CCl4. CCl4 I have drawn here. Is it polar or non-polar?
Non-polar.
It's non-polar. And be careful, we are talking about the polarity in the molecule, not in the bond. Okay, CCl4 has 4 polar bonds here. Okay, but the molecule is non-polar. So let's go to BCl3 and NCl3. NCl3 is like here. Okay, so you have N. Here we will have Cl, Cl, Cl. So is this structure polar or non-polar?
It's polar.
It's polar, exactly. Pyramidal structure is polar. If the bond is polar, the trigonal pyramidal structure would be polar. So the answer is this one. But what is the structure of BCl3? If you remember, the BCl3 has trigonal planar structure. Boron has only 3 electrons, and when it shares its 3 electron, nothing remains for itself. So it becomes BCl, Cl, Cl. So it has trigonal planar structure. You have 3 polar bonds in this direction, but they cancel out each other. So the molecule becomes non-polar. The answer is NCl3. Okay, question number 11 says, which is the best description of the carbonate ion? CO3 2 minus.
C.
Which one?
A.
C.
Okay, so you have to draw the Lewis structure to know that. First, the carbonate has, okay, let's draw it very fast here. Total valence electron, carbon is 4, 3 oxygens, 3 times 6. You have 2 negative ion, so the charge is 2 minus, so we add 2 electron here. So it becomes 24. You have carbon, oxygen, oxygen, oxygen. You put the lone pairs here. The number of the electron here is 26, so you have to cancel one of them, bring from the adjacent molecule here. So you have 3 resonance structure, but we don't need to draw all of the resonance structure. So this would be the Lewis structure of the carbonate. How many domains do you have here?
3.
1, 2, 3. So when you have 3 domains and no lone pair, your structure would be trigonal pyramidal like this one. So planar trigonal, sorry. And the bond angle is 120. Okay, so it's like this, C double bond O, O, O. This is the structure. Okay, any question?
Teacher, for question number 9, مگه ما نگفتیم مثلا برای گروپ 1 اگه به سمت پایین بریم پایین گروپ الکترونگاتیویشون بیشتر میشه برای
No. For group 1, when you're going down the group, the electronegativity decreases.
it increases.
Why? Why increases? when you are going down the group, the molecule becomes bigger. So when the molecule becomes bigger, their electronegativity decreases.
من آخر کتابو که خوندم نوشته بود که tendency to lose electrons and form positive ion increases down a group. برای
Yeah, it's a
group
tendency to lose the electron. It means their ionization energy decreases. It's easier for them to lose the electron because the nucleus doesn't have the power to attract the electron. Same thing in electronegativity. When it shares the electron, the nucleus doesn't have power to attract the electron, so it's easily lose the electron. It means electronegativity decreases. Okay, so that's losing electron or not. It's about ionization energy. Their ionization energy decreases when you are going down the group. Their electronegativity also decreases when you are going down the group. Same thing for group 17. When you are going down the group, the electronegativity decreases. Okay, so go and revise one more time. Electronegativity when you are going down the group decreases because the effective nuclear charge remains almost same for the group, but the electron is farther away from the nucleus. So the ability of the nucleus to attract those shared electrons decreases. So when you're going down the group, the electronegativity decreases, the ionization energy decreases as well. Okay?
Thank you.
Okay, question number 12 says which molecule contains polar bonds but is non-polar?
B.
The B, exactly. Okay, we had the example here. Here I have deleted that one. So CCl4. Okay, it has polar bond, but the molecule is non-polar. Okay, let's go to question number 13. It says which substance would be expected to have lowest electrical conductivity? Okay, so electrical conductivity, the first one, what type of the material is that? AL.
Metal.
It's metal, and you know the metal, they have very good electrical conductivity. Okay, it's one of their specific properties. Part B, Al2O3, what type of the material is that?
Ionic.
It's ionic. You know that the ionic in the solid state, because their ions are fixed in their position, they don't have electrical conductivity. But here, the point is that it's liquid. It means you have melted the aluminum oxide. When you melt, the ions become free to move. So they become electrical conductive. Okay. In part C, what type of material is that? MgCl2?
Ionic.
Ionic. Again, the point is that it's AQ. What does it mean? Means it had dissolved in water. When they dissolve in the water, again, the cation and ions separate from each other and they become free to move. So they become conductive again. So part A, B, and C, all of them are electrical conductive in the state that they given, in the solid, liquid, and aqueous. But for the last one, HCl, what type of the material is that?
Ionic.
No,
Covalent.
covalent. It's molecule, yeah. It's a molecular compound, okay? And the molecular compound, because you don't have the net charge on the molecule, they are not electrical conductive. No matter they become in solid, gas, or liquid, they are not electrical conductive, like the water, like the carbon dioxide, like HCl in the gas. But there is only one exception for the covalent compound that is electrical conductive. What was that? Last session we
When
talked
they
about.
dissolve in water.
No, even when they dissolve in the water, they don't become conductive. For example, alcohols, when you dissolve in the water, both of them are molecular compound. They don't have any ion to conduct the charge. Okay, the exceptions was carbon. Some allotrope of the carbons, like the graphite and graphene and carbon nanotube. These three are giant covalent structure, but because they have free electron, they are conductive. Okay. So the molecular compound, or the compounds which have the covalent bond between them, like the giant molecular compound and the molecules that are not electrical conductive, but some allotropes of the carbon that are very good electrical conductive.
Here, I should add that some of the molecular compounds, like HCl that you have here, when you dissolve them in water, they ionize or they dissociate to cation H plus and anion Cl minus. In that case, when you dissolve them in the water, the solution become electrical conductive. But the generally molecular compounds which you dissolve in the water, they don't dissociate, they don't ionize, so they are not electrical conductive even when you dissolve them in the water. This properties is mainly for the acids. Another example, we can have, for example, CH3, COOH, acetic acid or ethanoic acid. When you put the acetic acid or ethanoic acid in the water, the H plus ionizes from the molecule. So we have H plus and CH3COO minus. But acetic acid is the weak acid. It means it doesn't completely dissociate. Only a small part of the molecule dissociates to H plus and CH3COO minus. So the amount of the ions which produced for acetic acid is very small, so the solution become conductive a little bit, but for the HCl it dissociates completely to H plus and Cl minus, so it will produce a lot of ion in the water and the solution become electrical conductive. But generally, as I said, we can say the molecular compounds, because they don't have the net charge, they are not electrical conductive in the solid state, in the gas state, in the liquid state, and also when you dissolve them in the water, unless they produce the ion or they ionizes to the cation and anion in the water.
Question number 14 says, which substance can form intermolecular hydrogen bonds in the liquid state?
B.
Yeah, exactly. So when you say the OH hydrogen bond, the alcoholic functional group, you must know that they can form the hydrogen bond between their molecule. Okay, so this one we have talked about, that one CHO. This one doesn't have the phone element, but what about this one, CH3O CH3? It's like the water. So in the water you have hydrogen and hydrogen, but in this molecule the hydrogen is replaced by CH3. So the hydrogen is not connected to the oxygen anymore. So this one doesn't have hydrogen bonding. So the answer is B. Okay, question number 15 says, carbon and silicon belong to the same group of periodic table. Describe and compare three features of the structure and bonding in the three allotropes of carbon: diamond, graphite, and C60 fluorine. Okay, so you had that table. Okay, so I won't answer this question because you had in that table and they compare their structure and bonding. For example, the structure of the graphite is layer by layer, and the domain around each carbon is 3, so the structure would be trigonal planar. For the diamond, you have 4 domain. Around each carbon, you have tetrahedral. Each carbon is bonded to 4 other carbon. C60 fluorine, each carbon is connected to other 3 carbon. It has 1 double bond, 2 single bond. So their structure, if they are layer by layer, they are sphere, okay, they are 3-dimensional structure, and the type of the bonding, you have all of them in the table. So I won't repeat it here. Let's go to question part B. It says both silicon and carbon form oxide. It says describe the structure and bonding in SiO2. Again, you had this one. Okay, the structure, it has tetrahedral structure. Each silicon atom is bonded to 4 oxygen atom. Each oxygen atom is bonded to 2 silicon atom. The bond between them is covalent bond. The oxygen acts as a bridge between the 2 silicon atoms. So you can explain this one. Part 2 says the silicon dioxide is solid, but carbon dioxide is gas at room temperature. Explain this one. Okay, who can explain this? why silicon dioxide is solid but carbon dioxide is gas.
اون جاینت اون یکی مولکوله.
Exactly. Silicon dioxide is giant molecular structure, and all of the atoms in the molecule are joined to each other by covalent bond. They are strong. It's not easy to separate them. So the attraction between base unit, which is atom, is strong. So that's why they have high they have high attraction between their base units and they become solid. But for the carbon dioxide, it's a molecular compound and it's non-polar molecular compound. Only force of attraction between its base unit, which is molecule, is weak London dispersion force. So it remains gas at room temperature. Part C says describe the bonding within the carbon monoxide molecule. Okay, bonding within carbon monoxide. This one. Okay, it says within, it means the bonds inside the molecule. Okay, you must say that they share 2 electrons. The oxygen shares 1 pair of the electron from one side from the carbon, so you have the coordinate bond. So I must explain about this one. Okay, so most part of the question 15 was available in the text directly. So that's why we don't remain on that one. Let's go to question number 16. It says methoxymethane, this is methoxymethane, and ethanol have the same relative molecular mass. So their mass is the same. Both of them are molecule. Explain why methoxy has much lower boiling point than ethanol. So both of them are molecular compounds. Methoxymethane and C2H5. So you must only talk about the intermolecular attractions which are available between them to explain why the boiling point of the methoxymethane is lower than ethanol. But before explaining that, what is the point of this one? It says they have same relative molecular mass. What is the point of that? What does this shows you when 2 molecules have same molecular mass?
یعنی لندن dispersion forceشون یکیه.
Exactly. So both of them are molecules. So all of the molecules, they have London dispersion force. But for these 2 cases, the London dispersion force are equal. So this difference in boiling point is not related to London dispersion force. Why? Why the ethanol has more boiling point than methoxymethane?
Because of hydrogen bonding.
Because of hydrogen bond, exactly. So you have hydrogen bonding in ethanol between its molecule, but you don't have in methoxymethane. So that's why methanol has higher boiling point than methoxymethane. Okay, both of them are so polar. So both of them have dipole-dipole attraction. Okay, but the main reason that the boiling point of ethanol is more than methoxymethane is the hydrogen bond. Okay, the hydrogen bond is very important. Question number 17 says CCl2F2 was used as coolant in refrigerators, but this use has been discontinued due to the concern about the destruction of the ozone layer. We will study how that has the effect on the ozone layer in the next chapters. So draw the Lewis structure for CCl2F2. Okay, so let's draw the Lewis structure for that. The total valence electron, the carbon is 4. You have 2 fullerene, each one of them has 7 valence electron, and 2 chlorine, each one of them has 7 valence electron as well. So what would be the total valence electron? 32. Yeah? Okay, so let me put my laptop in the, just for one moment, let me put my laptop in the charge because the battery is almost finished. Okay, so there is 32 valence electron. Carbon is central atom. You have Cl, Cl, F, F, and you have to make all of them octet. So I put the lone pair to make them octet. And if you count the electrons are 32. So this is the correct Lewis structure. Just predict the shape of the molecule and instead the bond angles. So what would be the shape of the molecule? For the shape of the molecule, you have to determine the domain. How many domains do we have?
4.
We have 4 domains. So both electronic geometry and molecular geometry is
Tetrahedra.
exactly. And molecular geometry is tetrahedral. I write TH. And what is the angle between the tetrahedral structure?
109.5.
109.5. Okay, so if you want to draw it, you have to draw it like this. Okay, and the angle is 109.5 degrees. Okay. Persisted giving you reasons whether the CCl2F2 is polar or non-polar molecule.
Non-polar.
Non-polar.
Is it polar or non-polar?
Non-polar.
Non-polar.
Polar.
Okay. Okay, so why polar? Why it's non-polar?
خب attraction F خیلی بیشتر از CL درسته؟
Exactly. So you have 4
پس
polar
همدیگه
bonds.
کنسل نمیکنن.
Exactly. But the dipoles that you have here is much more than the dipoles that you have here. So these 4 dipoles cannot cancel out each other. So if you add these 2 dipoles, okay, you get 1 dipole here. And if you add these 2 dipoles, you get 1 more dipole but bigger here. So look, these 2 cannot cancel out each other. Okay, so the molecule is polar, and the reason is that the dipoles cannot cancel out each other.
خب آقا اگه فلورین رو با کلورین یه بار بگیریم یا فلورین با کلورین دوتاشون یکی در میاد.
No, because look, the molecule is not like this. Okay, so they are not exactly in opposite direction. Okay, so you have to think 3-dimensionally. Okay, they cannot cancel out each other. Okay, maybe I can show you here. Let me see if I have the notes or not. Okay, so look at here. Okay, this is your molecule. Okay, so no matter where you put the chlorine, where do you want me to put the chlorines? Let's say, for example, 1 chlorine here, 1 chlorine here, and let's put the fluorine here, fluorine, no matter where you put. Okay, so you have 1 small dipole here, small dipole here, 1 big dipole goes inside, 1 big dipole goes up. Again, these 2, if you add them, it makes 1 dipole here. These 2, when you add them, it puts 1 dipole here. These 2 new vectors cannot cancel out each other. Okay, so they are not exactly opposite to each other. If the molecule was like this, okay, like the plus sign, you can see I can put 1 fluorine here, 1 fluorine here. The dipole of this one cancels the dipole of this one. But in the molecule you have this type of the structure. Okay, they are not aligned along. They are not aligned along each other. Okay, so you have 1 fluorine here. No matter where you put the fluorine, they are not in the same direction, so they cannot cancel out each other completely. Okay. Okay, part D says explain what is meant by resonance with reference to the Lewis structure of the ozone, O3. Okay, what was resonance structure? Okay, you know that the resonance structure is like this for O3. But what does it mean when we say we have resonance structure?
آقا یعنی میتونه اکسیژن یا با اون دبل باند کنه یا با این یکی.
Okay, yeah, it means when we have resonance structure, it means none of these ones is the correct structure of the molecule. Okay, the molecule is average of these 2 structures. So when the molecule cannot be shown by 1 Lewis structure, we say that we have resonance structure. We draw several structure, and the real molecule is average of all of those situations. Okay, part E says contrast and compare the bonds in O2 and ozone suggests why ozone may be more easily broken down in stratosphere. So this is ozone molecules, and O2 molecule is like this one. It says the ozone can be broken more easily rather than this one. Why? So this is contrast and compare. It means talk about their strength, about their bond length. So what can you say about them? Okay, do you have class after this session? After this block?
No.
You don't have class, so we can continue the class until we have finished the questions, if it's okay for you.
It's okay.
Okay. So, okay, so how can you compare the bond in O2 with the bond in O3? How can you compare? Okay, so for O3, you have 2 resonance structures. For O2, you just have 1. So what is the bond order here in oxygen molecule? Bond order is 2. What is the bond order here?
1.5.
1.5. Okay, so if you want to compare the bond between the oxygen and oxygen in ozone with oxygen, which one is stronger?
Oxygen.
Oxygen is stronger. Which one is longer?
Ozone.
Ozone.
Yeah, exactly. So the bond in oxygen is shorter and stronger. This one, shorter and stronger. Here, it's longer and weaker. Okay, so this means comparing and contrast. Okay, so it means, say this one is longer, this one is shorter, this one is stronger, this one is weaker. So this is comparing and contrast. So when you see the compare and contrast in the question, it means you have to compare them. Okay, so again, this suggests why ozone can be easily broken in stratosphere. Why it can be easily broken? Because the bond between the oxygen in the ozone is weak compared to O2. Okay. So any question about this one?
No.
So I think it's clear. Okay, so let's move on. Oh, we have a lot of questions here. Okay, so let's answer question 18 and then we leave the rest of the question for the next session. Okay, question 18 says Vesper theory can be used to predict the shape of the molecules. Explain the prediction of the Vesper theory in the following, including your answers, full Lewis structure, the name of the shape of the molecules, and the bond angles. So we have done this one in the videos. Only this one is new. Okay, so I only do for this one because the rest of them you know how to draw it and you had them in the YouTube videos which I put it in the channel. So CH3CHO. So the first thing, this one, you must know how the atoms are connected in CHO. In CHO, carbon is connected to the oxygen and is connected to the hydrogen. And also you have CH3. So in the CH3, you have carbon with 3 hydrogens. Okay.
آقا ببخشید
Yes.
این فانکشنال گروپ ها باید کلا حفظ باشیم؟
Yeah, in chapter 10 you will study about them. Okay.
خیلی
But
ممنونم.
for now you must know this one, CHO is aldehyde. You must know C double bond OOH, C double OH, and you must know the OH. Okay. So CHO I have drawn here. The acidic functional group is C double bond OOH, and alcohol functional group is OH. Okay, so for now you must know these 3. Okay, so but the structure which I have drawn here is not correct Lewis structure. In correct Lewis structure, you also must show the lone pair. The only lone pair that you have here is on oxygen. Oxygen has 6 valence electron, 2 of them is gone for sharing, so 4 remains for itself. The carbon has 4 bonds, so it means all of its 4 electron is gone for sharing, both of the carbon. Okay, so explain. Okay, so this is the Furlewis structure, the name of the shape of the molecule and the bond angle. So here you have 2 carbons, so you can talk about the bond between these 2 carbons. So about the blue carbon, how many domains do you have there?
4.
4. So around this carbon, the shape is
Tetrahedral.
tetrahedral. 4 domain, all of them are bonds. So the carbon which is in black, in green, how many domains do you have? 1, 2, 3 domains. So the shape around that one is trigonal planar. Exactly. So you don't need to draw that one. You also just need to name the shape. Okay. But if you want to draw them, it would be like this. So for the carbon which is in blue, you have 4 domains in the tetrahedral arrangement. Okay, so one of these domains is hydrogen, 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 and the third one is connected to the carbon. This carbon has trigonal planar arrangement, so I can draw one of the domain here, the other one is here. Okay. So if you want to draw the shape, this would be the shape, but it's not necessary. But you must know that the bond angle here is 120 degrees, 120 degrees. Here is also 120 degrees. And the bond angle that you have here, all of them are 109.5 degrees. So this is the shape of this molecule. Okay, so we talk about the bond angles as well. Part B says only one of the molecules in A is able to form intermolecular hydrogen bonding. State which molecule is that? It's very obvious. Which molecule? In part A?
Water.
Yeah, water is a famous example. Okay, this one. State which molecule is and describe the features it possesses which make it possible for it to form hydrogen bond. Why it can form the hydrogen bond?
It's polar.
Because oxygen is bonded with hydrogen.
Exactly, because hydrogen is bonded with a very electronegative atom of the oxygen. That's why it can form the hydrogen bond.